Space, the final frontier. Now, we don't have starships just yet, but what we do have are satellite-based telescopes. Hypothetically, such telescopes could allow numerous researchers to peer into the unknown. However, in practice, access to such telescopes is fairly limited. This is due, in part, to the difficulty of manufacturing the mirror components necessary for light capture and focusing. These mirrors have to be perfectly polished, stiff, and lightweight enough to be launched into space. And as such, the process to create them is costly, time-intensive, and highly specialized. These are all areas that I aim to address with my research. To do this, I'm leveraging the flexibility of 3D printing. Now, 3D printing is probably a far cry from what many of us imagine when we think of, say, glass blowing, which uses a long metal blowpipe to form molten glass. My process is decidedly less dramatic, but it does offer some impressive advantages in terms of dimensional fidelity and geometric flexibility. I've developed a UV-active glass resin formulation, which can be printed and cured in much the same way as commercial plastic 3D printing. Because this material can be printed and cured at the same time, I've been able to use it to create shapes which have either been too complex or too thin to make with other methods of glass additive manufacturing. Once printed, I can thermally process these shapes into a transparent fused silica glass. Because fused silica can be polished to a very low surface roughness and also exhibits a very high stiffness and low coefficient of thermal expansion, it makes it an ideal material for use in satellite technologies. To demonstrate the robustness of this printing process, I have made a variety of test prints, which notably includes some of the largest glass printed at Livermore National Lab to date. To begin, I have been testing my process on geometries very similar to state-of-the-art mirrors which are currently in use in satellite telescopes today. However, one of the most exciting aspects of 3D printing is its capability to make shapes which are not currently able to be made with other forming methods. To this end, we have plans to combine complex stress simulations which approximate polishing and use conditions each mirror will experience throughout its lifetime, and use those to intelligently design mirror supports and then print them. This flexibility, the inherent accessibility of 3D printing, and the elimination of costly machining steps mean we can envision a bright future for 3D printed integrated optics. In a world where more researchers have access to satellite technology, we'll be able to boldly see what no one has seen before. Thank you.